Welcome to the Mechanics of Solids lecture series. In this series of videos, we're calculating examples using Mohrs circle. Our learning objectives are for a given plane stress state to evaluate the principal stresses, maximum shear stress, and angle of rotation to the principal axes using Mohrs circle. Also, we want to be able to apply Mohrs circle as a visual tool to validate stress transformations. And finally, we want to be able to extend Mohrs circle concepts to 3D stress states. Our first example, we're given a little stress block, and with stresses interpreted, sigma x equals negative 30, because it's pointing inward, sigma y equals negative 15, because it's pointing inward, and tau xy equals negative 35, because the shear stress is acting downward or negative on the positive x face. For this stress state, we're asked to plot Mohrs circle, find the principal stresses and the maximum shear stress. We're asked to find the angle of rotation theta p from xy to the principal axes and plot the principal stresses on a transformed view of the element. Finally, we're asked to determine the stress state at a rotation theta negative 15 degrees from xy state and validate the stresses by inspection using Mohrs circle. And we'll plot these stresses as well on a transformed view of the element. In this video, we'll do parts 1 and 2, and we'll do part 3 on the next video. So for part 1, we need to calculate a few statistics in order to be able to draw Mohrs circle. We'll start by identifying the origin. A equals sigma x plus sigma y over 2 equals negative 30 minus 15 over 2 equals negative 22.5. Therefore, our origin is located at A0, or negative 22.50 on the sigma tau axes. The radius of the circle is computed as sigma x minus sigma y over 2 squared plus tau xy squared. For this stress state, that would be negative 30 minus a negative 15 over 2, this is 30, squared, plus negative 35 squared, which gives 35.8. We compute the principal stresses, sigma p1, sigma p2. They can be computed as A plus or minus r, negative 22.5 plus or minus 35.8. That gives us two values, 13.3 and negative 58.3. We will interpret those values as the largest one. The most positive one will be principal stress 1. So sigma p1 equals 13.3. And the smaller of the two, or the more negative of the two, sigma p2 equals negative 58.3. And finally, the maximum shear stress in plane, tau max equals the radius equals 35.8. Okay, let's go to a next slide where I've summarized the statistics that we just calculated, and I have a plot here that we can use to plot the circle. The x-axis will be the sigma axis, the y-axis will be the tau axis. Now I always want to take and start by plotting the existing stress state on my sigma tau axes, where I pair sigma x with negative tau xy, and I pair sigma y with positive tau xy. Okay, this is just a convention, and we use this convention in order that the rotation angle on Mohrs circle is consistent with the direction of the rotation angle for our transformation. So sigma x, negative 30, I'm going to come over negative 30 on the sigma axis. Tau xy being negative 35, I'm going to plot the negative of that, so I'm going to come up 35. And there's my first point, sigma x, negative tau xy, which equals negative 30, 35. Okay, the second point, sigma y, tau xy, I'm going to come over negative 15. Oops. Come over negative 15, and then tau xy down negative 35. So my second point is located right there. That one is sigma y, tau xy, or negative 15, negative 35. Now I want to draw a line connecting those 2 points. Make that line as straight as possible. And that line will intersect the sigma axis at the origin of the circle. The origin, which is negative 22.5 and 0. And that does, by inspection, look to be right. If it's not right, you should go back and check your calculations and make sure they're correct. This is part of your sanity check. Okay, now we want to draw a circle that has, to the best of our ability here, has the same radius. Okay, so something like this. It's hard to draw a perfect circle freehand. If you have a compass, it's a good idea to use that to help draw a better circle. That's about as good as I can do freehand, but it looks okay. Let's check some other points by inspection. My principal stresses, 13.3 and negative 58.3, are the intersection points of the circle with the sigma axes. So the first one, sigma P1, equals 13.3. That's about right by inspection. Sigma P2 equals negative 58.3. That's about right by inspection. Notice that the shear stress is 0 at those points. The maximum shear, 35.8. That should occur at the top and the bottom of the circle. I'll just plot the one at the top. Tau max equals 35.8. By inspection, that looks to be about right, and that's very close to the starting stress state. Okay, let's also calculate the angle from our current XY state to the principal axes. And I'm going to eyeball it by sketching it on the circle first. I want to go from the existing X state, the shortest way that I can get to the sigma axes. So I'm going to go in the counterclockwise direction. So that, by inspection, this angle right here would be 2 times theta p, or 2 times the rotation to the principal axes. Now let's calculate it. Theta p equals 1/2 inverse sine of the absolute value of tau xy divided by r is 1/2 the inverse sine of 35 divided by 35.8, which computes to about 39 degrees. And so we'll say theta p equals 39 degrees. It's positive by inspection because on our circle the angle is counterclockwise. Now let's also validate this by inspection by looking at the circle. I can see this tells me that this angle to theta p should be approximately 78 degrees. By inspection, that looks to be about correct, so I conclude that my calculation is correct. Now finally, I want to draw the transformed stress state of the principal axes. So from X, I have a transformation to the principal 1 axis, which I'll label P1, and that is theta equals 39 degrees. The principal P2 axis would be 90 degrees from that. So my transformed stress block will look something like this. P1, P2. Okay? Principal sigma P1, 13.3. I'm going to draw in this direction, pointing outward. 13.3. Sigma P2, negative 58.3. I'm going to draw that on the other face, pointing inward. 58.3. And then I have no shear stress because these are the principal axes. So my transformed stress block looks like this. The maximum principal stress, maximum normal stress, minimum normal stress, and no shear stress. And we'll continue the last part of this example in the next video.